Hello and welcome to the Trusted Computing Group webinar entitled Using the TPM to Solve Today's Most Urgent Cybersecurity Problems. First off, we'll review some logistics. If you're having trouble hearing this webinar, please check to make sure that the sound is on your PC or device. Secondly, questions can be posed throughout the webinar. We will be holding those to the end of the session. But feel free to post a question as it arises using the question tab at the top. Today's presenters are two longtime Trusted Computing Group members. We first have Stacy Kennedy, Technical Marketing of Trustworthy Computing of Cisco Systems. Stacy, CISSP, is a member of the TCG Embedded Systems Workgroup. He also currently serves as the primary board representative for Cisco. He has worked in the field of trusted computing for a number of years and is a subject matter expert in trusted computing. His responsibilities require an in-depth understanding of the trusted computing market, including advances in hardware and software security, as well as vendor and customer market dynamics. Our second speaker today will be Monty Wiseman, Security Architect of Intel Corporation. Monty works for Intel's Data Center Group. His current projects include architecture for TCG, Intel's TXT technologies, BootGuard, and other security initiatives. Monty has participated in the TCG PC Client Working Group, Security Evaluation Working Group, and is Intel's representative in the TCG Technical Committee. Monty has over 20 years experience in desktop, network, and mainframe environments, holding security-related and other engineering positions at Novell, Fujitsu, and Control Data. He has been developing hardware and software computers ranging from mainframe to microcomputers since 1975. Stacy, would you like to talk about use cases?
All right, thanks very much, Lindsay. I'm going to move on now, and what we're going to do here is talk about several examples of products in the market today that use TPMs, and we'll talk about, we'll look a little bit into the future at what's soon to be in the market. So first of all, I'd like to talk about the Google Chromebook. Chromebook Chrome OS is an open source OS, and if you have interest in taking a look at what it's actually doing, you can follow up this call by going out to the open source community and seeing for yourself. So let's talk about what happens when you power on a Chromebook. The first thing it does is it uses a piece of code called the core root of trust for measurement to measure BIOS and store the measurements that it finds in TPM. Next thing it does is it validates the measurements of the BIOS against a set of expected measurements that are kept in shielded location in the processor. And when it does that validation, if it finds that everything matches as it is expected to match, the system will boot. If it finds a mismatch, there's a BIOS that didn't validate correctly, what Chrome OS will do is delete that mismatched BIOS module, go to a library of last known good versions of that module for all of the BIOS. Pull the deleted version, install the last known good version of that affected code, and then it will reset the system and measure again. It will go through that measure, validate, uninstall, reinstall, measure, validate loop until everything has a satisfactory measurement, and then the system will boot or it won't come up at all. Now, when we think this, if you buy a Chromebook, you don't have to set this up. Your company doesn't have to administer it. It's just the way the system works. It either comes up clean or it doesn't come up. And of course, there are update mechanisms so that if your corporation or you decide to update firmware using a valid patch, that can be handled, and the golden measurements reset, and the library of last known good can be updated accordingly. So that's an example of TPM in use in the market. But how about something a little bit more popular than a Chromebook? How about Windows 8? Let's talk about that. In the evolution of malware in the Windows system, we've seen malware go lower and lower in the stack, earlier and earlier, appearing earlier and earlier in the boot sequence, finally transitioning out of Windows altogether and into firmware. Microsoft needed a way to address this problem, and so they took several steps in this rather complicated slide to make that happen. One of the things that Windows 8 requires in any PC or any other end device that runs Windows 8 is the firmware must implement UEFI secure boot, and we see that reference there under the number 1. So UEFI secure boot is a nice thing, but it doesn't measure or validate all of the BIOS inventory, only part of it. So there's still a window of exposure here. To try and address that, Microsoft also requires a TCG-style measured boot. That means that BIOS, the entire inventory of BIOS and the OS loader, and some of the very early code that is part of the Windows operating system, all have to be measured using what I mentioned before, the core root of trust for measurement, and those measurements have to be stored in the TPM. Now, Windows does not validate these measurements at this time. Later on, and in the future, this isn't implemented by Microsoft yet, it's a roadmap item, but in the future, when this PC that just came up supplicates to join a network, at that point, a validation server that Microsoft intends to make available will demand an integrity report from this PC. That is, use the TPM to sign those integrity measurements that you made when you came up. Give me that report. I'm going to check and make a decision about whether I can trust you or not. And if the decision is yes, those measurements are good, then you can join the network. And if the decision is one or more of those measurements is bad, you will not be allowed to join the network. You'll be diverted to a ranking network, or something else will be done in order to respond to the infection on your PC. So what Microsoft has done by using this measured boot mechanism and their early launch anti-malware, their ELAM referenced in number 2 there, is they are trying to span the gap from the moment you press the power on key to the time the security suite that is installed in the Windows operating system can take control and protect the system from then on. There is opportunity for mischief in that span of time from the time you press the power on switch to the time the security suite starts. Measured boot and ELAM are Microsoft's efforts to close that gap. All right, so moving on, we've got a product from the Air Force Research Laboratory, AFRL. The problem they are trying to solve here is a cost control problem in the Department of Defense. If I'm a worker in the Pentagon and I have access to a top secret network shown in red, a secret network shown in, mustard, I guess, confidential network shown in yellow, and I like sports, so I want to go to ESPN shown in green. So those are networks that I have access to as part of my job in the Pentagon. So today, that means I have 4 different PCs on my desk, each one with a wired connection to one of these networks. So we've got an air gap. The idea is that there can't be contamination of the contents of one network into the contents of another network because I have 4 different PCs. And that sounds great from a security point of view, but the Department of Defense spends $8,000 per year per PC to administer these. So for me to have this configuration of PC on my desk costs us, the taxpayers, $32,000 a year. So AFRL set out to try and figure a way to consolidate 4 PCs in this particular case down to just 1. So they use TCG technology as implemented by Intel on their vPro chipsets. Intel vPro specifically using TXT It's a mechanism here, trusted execution technology. We have a Zen hypervisor running on this PC, and this is a standard stock PC. It could be from any of your favorite OEMs. This Zen client is aware of the security hardware, is aware of trusted execution technology. When that hypervisor starts, it also starts a set of service VMs as indicated here, and all of this stuff in blue is validated at the time of boot using Intel's technology based on TCG specifications. If any measurement for any of this blue code doesn't validate, the system won't start. Does start is starting in a known condition as established by the Department of Defense, in this particular case, the customer. With that environment up, you've got a hypervisor, a set of service VMs. With that up, then the guest VMs start, and we have one PC doing the job of four previously significant systems. For the taxpayer, and AFRL will sell SecureView to anyone who wants to use it, and there are some competitive products in the space now that do the same thing, basically the same kind of architecture, but different software underneath. Okay, so that covers three examples of what's being done in space today, what you can buy today. And now we're going to take a look into the future here. If you think about what was done by AFRL, they were implementing hardware-based security measures from Intel to secure a hypervisor and then using hardened hypervisor to securely launch a set of VMs. Well, there isn't necessarily a whole lot of conceptual difference between an endpoint and the server in this particular case. So why can't we do this kind of thing in servers? Well, there are some technical issues that kind of make it harder, but stuff can be done, and that's what we're talking about here. We're getting set to talk about, well, okay, can we do this in a cloud? Yes, you can. You can do it with VMware as the basis for your hypervisor and your software stack, and you can also do it with OpenStack. And if any of you have people at Cisco Live this week, that's where I am right now. I'm speaking to you from San Francisco. There are 25,000 people here, and a few of those people are representatives from Intel and me in the Intel booth where we can show you this architecture. What we have available here is we have Intel's hardware enforcing security and integrity on the hypervisor. The hypervisor then comes up and uses similar techniques to validate the security of virtual machines to come up so that we know what the operational state is when these machines go live. To look at what might go wrong, here's the model of what might go wrong. It might be that an attacker comes in through a VM, compromises that VM, and it is conceivable that he can break out of that VM and either compromise the hypervisor or compromise VMs that are adjacent to him, as shown here. So that brings up the state of the conversation about the state of the art right now. And the state of the art is that we have specifications, hardware-based security implementations that can validate the integrity of software when it launches. But when it launches is only part of the problem. We also need to be able to validate the integrity of the operating environment in execution. After all, especially in a cloud environment, we may be down as much as 15 minutes a year. That gives ample time for mischief to be made. Now, TCG has specifications that are in an advanced state of authorship called a dynamic runtime measurement, DRTM. And the point of DRTM is a hardware-based mechanism for validating the integrity of an operating environment in execution. We aren't quite there yet, but there are mechanisms that can do this as well. So if you take a look at companies like Trapezoid, Virtuata, NBS, and tripwires, sort of, kinda, you can find that there are software mechanisms that can be installed into either a hypervisor or a VM. Once they are up and operational, they can be used to attest to the ongoing integrity of the system in operation. And this is another, if we cycle back and remember what Windows 8 is trying to accomplish with their measurement and their approach, they're trying to span the gap between start of the system and start of the security software that protects the system. And we can apply the same logic here to the hypervisor and VM. We're using hardware technology to validate the integrity of the system up until the security suite takes over. And if that security suite includes software to validate the integrity of the operational system, the state of the art right now. That's the best you can get. And then finally, we've got one other use case here that we should see more of as the future unfolds. And here, this is the Internet of Things, and we're talking about how do we help devices that are part of the Internet of Things understand stranger danger. You know, right now, if you can't establish a session with a device that's got an IP address, then it will respond to any valid command that you give it. It's highly likely that the device may not even require authentication. So it's perfectly happy to cooperate with anybody who talks to it. And if that particular device is a power meter, or if it controls a pump in a pipeline or something like that, that's not really a good solution. But it is the solution that we are faced today. So what might we do about that? Well, if we were to incorporate a TPM into that device, that TPM can conserve an identity. For example, an asymmetric private key. It may be that with a little bit of extension to the protocols that are customarily installed in these devices, that the device will demand an identity from a person that's trying to set up a conversation with it, an identity that it recognizes, and it may also demand an integrity report from that individual. In other words, we can teach the device to only talk to people it knows, and only if it believes it can trust them at the time. Well, okay, how's that again? Well, you know, it may be that you and I have had a long-term relationship. You recognize my voice. You know that it's Stacy that's talking right now. But what you don't know is Monty, who has flexible ethics, is holding a gun to my head right now. Therefore, he is influencing my behavior. You know me, but you can't trust me. So in the machine world, you recognize the digital signature coming from the other end of this IP connection, so you know the person. What you don't know is whether malware has been installed on that system and is either monitoring the connection or is modifying the behavior of the person that you recognize, the machine that you recognize is there. So here we have a meter talking to an industrial control system console. They share certificates. So they know each other. They share integrity reports. So they recognize that they are both intact. Their integrity is valid. Therefore, they will conduct business with each other. An unknown operator attempting to contact that same meter does not have a recognized certificate. May or may not have a recognized certificate. Could have stolen one. But then, how does the attacker provide a valid integrity report? Well, you know, it's got to be digitally signed, and you know, there's some problems there. So the point is that in this kind of a model, the operator, the owner of this deployment of internet devices, can create a closed network in which the devices speak among themselves and speak to the industrial control system console, because they recognize one another and because they have validated that the devices that they are talking to are operating in a known state. Their integrity is understood and considered to be valid. All right, so that's me running through use cases with a little bit of crystal ball gazing, and now I'm going to turn the conversation over to Monty.
Hi, yeah, thank you, Stacy. That was a great introduction to how TPMs and TCG technology is used using real-world examples. And I really appreciate that. What we're going to do now is go through a little deeper and explain how TCG technologies actually perform these functions, and kind of segueing, and that was a great segue into some real world examples of the lower case, the little person on the lower case of this previous slide, that we really do have real use cases or real incidents of attacks happening on these devices, and some of them are shown on this slide. I won't go into a lot of detail, but there's both research, and of course research sometimes leads to attacks, or is a good indicator that while the research is above board and public, there's a lot more research that's done that's not necessarily as public. So anyway, these are just a few. There's actually another couple pages of this kind of thing that's going on. So let me go into some definitions, a little deeper set of definitions. And again, this is dovetailing nicely on what Stacy said, was kind of mapping what he discussed earlier as far as the device identity. We're going to call that more generically, there's an immutable component. Once this thing is manufactured, with the exception of hardware attacks, which are really out of scope for trusted computing, at least the protocols, with the exception of the hardware actually is an immutable component, and it is what it is. On the other hand, all devices are really a composite of both hardware and firmware, and the firmware is mutable. It's the reason you do it in hardware, or firmware, and not hardware. Is you want to be able to either reuse the hardware in different SKUs or different applications, or you want to be able to update the device in case there's a new feature or vulnerability found. So you don't often burn a lot into hardware, and you provide these features in firmware. But the problem with providing this in firmware is you no longer have this hardware-based assurance of what this device is. You know what the hardware is, but you don't necessarily know all of its behavior higher than the hardware in the stack. Right? So, and one of the problems that we have, just as identified in this next slide here, is just as an example, if I had this one hardware component, maybe it's got version 1, and I ask version 1, or this firmware, what its version is, it's of course going to respond back, yes, I'm version 1. And of course, if I update this component to version 2, it will, and I ask the question, what version are you? Are you 2? And maybe it'll answer version 2. And maybe the reason you did this update is there was a vulnerability in version 1, and you wanted to avoid this vulnerability by updating the firmware. But one of the problems we have here is that if in fact you have on the right-hand stack here, it's possible that the attacker would attack version 1 and take over version 1, but of course it's not going to say it's vulnerable version 1. It's in fact going to report back that it is it's version 2. Therefore, somebody on the outside would trust it when it's actually not trustworthy. So what we're doing, what TCG technology does, is it's providing that a level of attestation below the firmware that provides the assurance to the end user of what firmware is running. TCG doesn't control what firmware is running, though and I'll describe the differences between verified and measured boot in a few slides. But what it does do is it says this is what ran, this is what executed, and you can have assurance in what that component is. So so how we do this is we have this concept called a root, and there's various roots that we define. I'll define a couple of them, but we define a root, and we place this root inside this hardware component. And what happens is the root is its behavior is undetectable. And so, we don't have time to go into the details here, but we have, in TCG, we have a concept called certificates. And the certificate talks about the origin or the properties of the root. And the root has a key associated with it, and you know which hardware component of which root you have, and there's an association between the root, the certificate, and that key, and you'll be able to prove what root that is. Now, once you've done that, now you can go and start inspecting, and this is what TCG adds, is you start having the ability to get an audit of or inspect the visible, measurable components of the firmware. Now, what I mean by visible, it's not necessarily visible. You can't look into the firmware from the outside point of view, but you have an audit trail, and this is what the TPM provides, is a testable audit trail of what this firmware is. So even though you can't necessarily see the source code of these firmware components or even the binary image, you have an attestable audit trail of what that firmware is and the identity of that firmware, so that you can tell if it's the firmware expect, for example, is it V1 in the previous slide or is it V2 in the previous slide? You'd be able to tell that without having to go through and actually dissect the platform itself. And so what we have here is, and I won't go through, I just wanted to provide this for reading later, is really the definition of a root of trust, is a component that performs one or more security-specific functions, such as measurement and or update, is trusted behavior in the expected manner because misbehavior cannot be detected under normal operations, and I won't go through the detail. But, I mean, the summary is that we have defined a set of roots and the behavior of those roots and the attestation properties of those roots so that one would be able to discern and obtain the identity of the firmware that's running above it or the other components that's running above it. So what are those properties, right? So what the basic TPM description, and this is as fundamental as we can get, is that you have a set of TPM commands, and generically we call these capabilities, protected capabilities. And they operate on a set of shielded locations which are instantiated as TPM objects. So what we've done is, and most people think of a TPM as just this, TSSOP28 or whatever, but really generically, this is what a TPM is, and it can be instantiated in many different ways, as I'll cover in a subsequent slide. And so the core definition of a TPM is you've got a standard set of operations that appear in the library spec, and those are the only ones you get to do. And those operations are the only ones that are allowed to operate on these objects. So we provide this fundamental set of operations, and the property you see on the right-hand side here is that there's nobody else by this little red arrow. There's no other agent that can get in here and interfere with the objects or the operations of the commands. And this is important because the firmware, you don't want the firmware that you're reporting on to be able to manipulate the audit, the digest or the audit trail that is reporting on it. Otherwise, you'd be able to lie about what you were. Right? So this is the fundamental property, and one of the things I want to make sure we get across here, especially as TPMs start going beyond PCs and into things like Internet of Things and mobile devices, is that a TPM doesn't have to be exactly instantiated exactly the same way that we do in a PC. And again, I've got some slides later on to talk about that. So let me touch on a little bit and clear up some misconceptions about the difference between verified boot and measured boot. And I actually don't like the term secure boot. I think that the term secure boot is a little misleading, although it's often used to mean verified boot. But I prefer to use the more specific terms of verified boot. And actually, let me go to the next slide because it's actually will show graphically the differences between these two. In measured boot, well, just insecure boot is just on top. We just do an arbitrary jump to a reset vector, and it's going to go along the way. And we certainly hope when you get to the OS and the apps that things happen the way you thought they happened or expected to, but there's no proof and there's no enforcement of these sets of actions. Measured boot, though, what we add is the ability to, and that's what these angled arrows are meant to depict. In measured boot, starting from the reset and starting from this immutable hardware, what we're doing is we are performing what's called a measurement. I'll get into a little bit more detail of what that is in the future slide, but we will perform a measurement operation into this bank vault, which is a TPM depicted as a bank vault. I'm just trying to be generic here. And we're producing a set of measurements into the TPM, which, as I discussed in the previous slide, is outside the reach of this firmware. So the firmware can't alter the measurement in any way. So you transfer control to this component, and then this component is going to transfer to something else, and it continues the measurement. And what happens is at the very end of this operation, what you end up with is remember I mentioned a key earlier. There's a key associated with this TPM. And I'm able to digitally sign a report of all of these measurements and report them to either the user or the IT department, whatever, as to what exactly ran. And so what we're showing here is that in measured boot, which is really supported by TCG technologies, is the policies as depicted by the certificate are applied after the system boots or somewhere in the process of booting, but most likely we visualize these at the end of the process. What firmware was executed, what OS was executed, as opposed to verified boot, which is depicted on the bottom. Verified boot, which is more on the UEFI, if you're familiar with UEFI technology. UEFI has, they call it secure boot, but I prefer verified boot, where what they're actually doing is they are enforcing the policy along the way. And so this is protecting the platform along the way from unauthorized software, but at the end, the IT really has no proof of whether this thing booted properly or not. That's what measurement is for. That's what TCG technologies are for. So really, we think the best of both worlds, the best combination is combining measured boot and verified boot. But that's really outside the scope of this discussion. I wanted to make sure that everyone understood the differences between those because they're often misunderstood, and that what we're talking about in this presentation and in TCG technologies is in fact measured boot, this middle row. So how do we accomplish this? So in the terminology that we use is simply, we have either proof of a device's identity, and this is one thing that TCG does, is we can just answer the question, is this the right device? Without regard to answer the question, what firmware ran, right? And so this is simply using, platform authentication, right, is proving the device's identity, and just simply using this key. What TCG allows also is the addition, as I've described in the previous slide, is the ability to add to that digital signature the set of the identity of the firmware components, and this we call platform attestation, right? So platform authentication is on the top bullet or the top portion of the slide, and the bottom one is attestation or platform attestation, where we identify the platform itself as well as we identify the firmware components. So I want to add a disclaimer here that even though I don't have slides or we don't have time to get into the detail, All of this is done, even though I'm discussing one particular key, it's actually a little more complex than this. And the reason for the complexity is we have built privacy into all of these protocols. And there is, in fact, even though it's simpler to discuss during this presentation and an introduction, one key, there is, in fact, a layering of keys associated with this. And that complexity is mostly, but not, there's other factors as well. But the additional set of keys is to enable user and owner privacy across multiple domains. And again, that's outside the scope of this discussion, but at least I wanted to make sure I mentioned that. At least anyone be very concerned about some privacy and single key usages. All right, so I talked earlier, diving in a little more detail about the actual mechanism and how this works. The actual mechanism is just we use cryptographic hashes, and in the upper right-hand corner, the actual operation of the measurement operation is depicted, where we simply start from a known value. All PCRs start at 0 at platform reset, at this depicted by this brick wall on the left-hand side, and so that's the property of TPM reset, which is also associated with platform reset. And what we do then is we take the measurement of the first component and do an extend operation. We don't have a write, and PCR stands for Platform Configuration Register, and there's a whole bank of them inside the TPM. Or there can be only one, it depends on the platform. But what we do is we take the existing, the present PCR value and append what you're going to measure into it. This is the extend operation. This is the hash, for example, of the firmware. We're going to hash those together. So, for example, if we were using SHA-1, you would have a 20-byte value of zeros for the first measurement, and you would append to that 20 bytes of the first hash of the first component, and then you would hash those together and replace the PCR value with that hash. And that's how this works. And again, what we're doing here is depicted on what we end up with is depicted on the left-hand side. You've got a key that's going to sign this PCR value, and this key is provided by the undetectable portion, right? But now we're going to relay to the outside world a signed the signed value, the resulting value of this PCR. And as you can see, if you're familiar with the hashing operation, you can actually accumulate these so that you actually really only need one, and you could build these up, and someone wouldn't be able to go back and replay a previous version and insert their own value because of the properties of a hash. And therefore, one would be able to provide a cryptographic evidence of the visible portions of the firmware without having to actually expose or having to evaluate the firmware itself. You simply provide a cryptographic proof of exactly what ran. All right, so I'm going to have to speed up along here and get into some of the, not sure where it went, it bounced twice, sorry about that. So just to give a real world example, and I'm going to go through this rather quickly, how this works on a PC is that you start with the root of trust for measurement, and we measure the BIOS, and then the BIOS would then walk to the post. It would post all these option ROMs, and all of these things, and then the option ROMs would run. And actually, the option ROM don't go to the OS loader. The BIOS does. Just try to make a simplified diagram. But you walk through this entire sequence and extending all these measurements into the various PCRs. And one of the things we've done is for each platform class, we have created a set of platform-specific specifications so that IT shops, for example, would be able to parse through and perform these attestation operations for the particular areas of the platform that they're interested in if they so choose. So one of the things we've done in the platform or in the PC client specification for UEFI, for example, is all of the measurements for the BIOS will go into PCR 0, and 0 just PCR. So as I said before, there's an array of these PCRs. They all start with 0 at reset. And then the option ROMs go into PCR2 and the OS loader into 4, right? And this is an example from PC client spec. Other, like mobile device or Internet of Things, might have fewer PCRs and might map them differently, but the concepts are still the same, right? So if an administrator was only interested in what OS loaded, they would get an attestation of PCR4. If, on the other hand, they were interested in going all the way back to the BIOS, they would want to get an attestation of PCR 0, 2, and 4, for example. So that, again, that's just how we have broken the specifications up. So again, leading to the fact that the PC client isn't the only type of platform that can have a TPM. What I wanted to do was to be able to depict not just different ways of doing it on a PC, but different ways of implementing a TPM in general, right? Again, you don't have to have a discrete chip to be a TPM. Among the ways to do it, that's one of them, and that's depicted on the left-hand side, where what you have is a discrete IP block, such as a chip. You've got an interface depicted on the top by this blue arrow. And again, if you're looking at a PC, this would be specified out in what's called the platform TPM profile for PC client. More specifically, this is an address FED41000s, just to be very specific. So if you go to that address on a PC, you will be talking to the TPM, right? And that's implemented in a discrete block, for example. And no other interfaces, as depicted on this right-hand, this arrow on the right, this red arrow, no other interface can get into it. The only way to get to the TPM assets is via these TPM commands via this one particular interface. On the other hand, what's depicted in the middle block here is it's entirely possible that some, even on a PC or on other types of platforms, you might have a dedicated IP block. And maybe they're inside of some other larger some other larger package, but it's entirely possible to design it so that you might have one IP block being maybe the core CPU, if you will, and then another IP block implementing the TPM functionality. And again, we've depicted the separation of function, which is what's required, and so that there's only one way in to this particular IP block, and that's what must be maintained. On the right-hand side, we're depicting even a more general implementation, and that is you've got a single hardware domain, but you've got separation of function, and there's a number of ways that this is done today, in that you can actually have the same hardware and having the hardware have the ability to have separate hardware domains and partition it between the two. And again, the requirement is that you provide some mechanism such that the only way on this hardware domain on the right-hand side cannot get to anything on the left-hand side except via issuing these commands through this defined interface. And again, this defined interface would be architected and defined by who's ever providing this package, if you will. And I show this on a separate slide, not that I just couldn't squeeze them and make them readable, all four of them readable on one slide. None of them are hierarchically different than the other ones. But I also wanted to show that, and I think Stacy alluded to this earlier in his discussion, it's entirely possible to do this with the VMM. And this is very similar to the one on the right-hand side, where you've got domain, you use a virtual machine monitor or hypervisor to perform the domain separations. And in this case, you've got a TPM that's inside of a virtual machine, a trusted partition, and it's in fact providing the services for the other VMs and the OSs and VMs. And you would do this, for example, on a server. The TPMs are not real fast machines or fast components. So if you had a hardware-based TPM, having all of these virtual machines compete for the one and only one TPM that might be on that system, first of all, you don't have redundancy and failover that servers require, but also there's some performance issues. So there's a number of initiatives and papers published today where one would be able to create a virtual TPM or a TPM inside a virtual machine that is in fact attested to by the hardware TPM. But again, we don't have the time to go into that discussion and how that works into this presentation. So let me get into a little more detail about the layering of the specifications, and if you're going to, go understand, go look at, okay, so what does it do to create an app or create an OS or a platform that uses TPMs? People think, well, I just go get the TPM library spec and I'm done, and unfortunately, life isn't quite that simple. There's the library spec, and the reason we created this specification as a library spec on the very bottom I'm pointing to is to enable all of these different kinds of platforms. So we didn't want to just create a TPM that would be only for a PC client, right? For example, we wanted to be able to create a TPM and have a TPM technology applied to servers as well as things like a tablet or a cell phone, or even all the way down to Internet of Things or embedded systems. And some of these, especially on the lower end, some of these platforms don't have the requirement for all of the protocols and the very rich set of policies that we envision might be required in a PC client or in a server. They don't need all of these features. So we created the TPM2 spec as a library. Think of it as if you're familiar with Windows, kind of a DLL, where you've got all of this either dynamic or static library to choose from. That doesn't mean you have to use them all. They're just available for you if you want them. And any of these, like for example, embedded system, I think there's 103, 105 commands specified in the TPM2 library. Maybe they say they only need 30 of them or maybe 20 of them, in which case those particular devices would simply not implement those other 100 or 80 some odd commands, and certainly wouldn't need 24 PCRs, which is what's in the PC client. Maybe they only need 2 or 3 of them, right? So at the very bottom is the library spec, which defines the lower layer behavior, right, and defines the structure and meaning and syntax and semantics of this byte stream as being depicted on the right-hand side of this diagram. So, but somehow you have to be able to marshal, you have to get the commands into the TPM itself. And this is done via the various platform interfaces as depicted by this other set of interfaces above in this kind of reddish color. And then above that, you've got a writer's guide talking about the driver, and then the TSS itself. TSS being the TCG software stack. T not being trusted because that area is not trusted from a TPM perspective. And then, of course, on the right, I'm showing the platform-specific firmware specifications. So what you really need is if you're going to build something from the ground up, you need all of these specifications. But of course, this would be far too complex for an app developer. So what we're doing is we're reducing this down, and this is all on the bottom part. This will all be provided by your OS vendor. And what we're doing is defining an upper TSS layer for applications. And what we expect to be developed is to have, for example, Linux keyring, a set of simple Java classes, PKCS11, all be ported to this TSS layer so that you've got, on the bottom part, you've got a set of experts that would be providing, all of this stuff depicted in this, in this bottom part. And this would only have to be done by, Linux and Windows and your operating system vendors. And your application layers we would expect to be provided just an extensions to these sorts of interfaces, as well as TSS is going to provide its own set of feature and API layers on top of that. All right, so let me walk through some of the usages, and I'm not going to go through the exact detail of how all these work. This is kind of reading material for you later on. But what I've done here is simply broken down into 4 categories of use cases for you. And again, I'll just introduce them here, but I don't have time to go through them in detail. But what I'm really doing on these top 2, and I probably should have colored them a little differently. These top 2 are all about device attestation, or really device identity and authentication and device attestation. Where in the first use case would describe, I want to, regardless of the OS or the firmware that's running, I want to be able to trust the device. Is this the device that I'm talking to? And so this row would describe exactly how that's done. And again, I don't have the time to go through this in detail. And the next row then, device and software attestation, leverages off of the key that we're using in the very first row, and then adding PCRs to the mix. And what I'm trying to show here is that once you've got the key, and now you've got it's a fairly small leap to go from just having this key, which attests to the hardware, to now adding the PCR values, which would not only attest to the hardware but to the firmware. And the difference between the attestation description that I described in the top 2 and the storage description, which I described in the bottom 2, are we really have 2 classes of keys inside the TPM. And the first class is a signing key, where I can prove to somebody on the outside what, in fact, is running, the device's identity or what's running. These latter 2 speak to, the bottom 2 rows speak to, I have also the ability to use an encryption key or a storage key to protect the assets on the system while they're in the field, so that somebody either can't take the information in the BitLocker example that Stacy spoke to in the first part of this presentation. I can say, well, this data, if someone copies the data off this device, well, the key's on the TPM, and you're not going to get the data because it's encrypted with the key protected by the TPM. And I can also protect, even on that same device, against somebody loading an unauthorized firmware and software, an OS, onto the device. I can protect the key on the individual device itself using the very last one. Okay, so I want to leave some time for some questions. So this is really depicting the second row, a sample protocol of how one would do that, where just as a very high level, the IT shop would get from the device manufacturer, for example, using the NIST 800-155 draft specification coming out, a set of PCR values or expected PCR values from the device manufacturer, and this would now be on the IT's BYOD list, for example. And the employee would then take that list, go to the retail store, buy it, and now would go through this protocol that, again, I'm not going to go through here, but it's provided for you so that you can walk through this. And the IT shop can, in fact, using this protocol, verify that it is, in fact, the device. The device is running the proper firmware and operating system. Now it can provision an encryption key to that device. And now the device proves that it's protected, that for example, BitLocker, for example, or full disk encryption. It can prove that this is in fact the key that's being protected. Now the IT shop, after going through this protocol, is confident in sending the information to that device. And again, this is more for kind of an offline discussion. And we would expect to have some sort of white paper associated with how this is, the details of how this works. All right, let me just real quickly scan through some of the features that these are enhancements to 1.2. We've already described the platform level attestation and security properties. What TPM2 adds is a flexible set of policies, and I'll go through that in the next slide. We've also added algorithm agility so that you're not just stuck with RSA and SHA-1, but you have the ability to have ECC and SHA-256, and it's extensible even beyond the ones that we've currently defined today. We've also enhanced provisioning. Let me go through some of those just very quickly. So we've added some of these new sets of policies, such as password and HMAC, and you can make time-based. You can restrict keys to only be valid for an hour, or you can say I can only use them once. You can also combine these policies together. And let me just touch on real quickly algorithm agility. As I said before, you're not just we achieve this by making an algorithm, basically a defined algorithm structures with algorithm types in front of each one of these things, followed by the cryptographic data. You can have that's supposed to be DES, by the way, not DAC. AES, you can have RSA, ECC, or various forms of SHA-1, and we have a registry defining these. And just real quickly, we found a problem with 1.2 is that platform manufacturers couldn't use the TPM because the owner was able to reset the TPM. So what we did was we broke the hierarchy or the TPM down into 3 distinct hierarchies, wherein each one of them is individually enablable. So I've left just a few minutes for questions. I'll turn it over to Lindsay.
Great, thank you, Monty. We have received a few questions throughout the webinar. First one, touching on Stacy's subject matter. Stacy, can you talk a little bit about the performance when doing an attestation as you illustrated in your embedded system example?
Okay, so in a constrained embedded environment, when we're talking about attestation, we're talking about the cryptographic hash of the inventory of firmware and software. So if you are in an environment in which you are very constrained by uptime requirements and start requirements, in other words, talking about, for example, an automobile where you got to start and be available completely in 2 seconds or less, then there can be some issues associated with integrity measurement. It does take some time. If you are not in that sort of an environment, if you've got 10 seconds to come up on the order of that, then caching the available firmware is not really a big deal. If you do have issues with instant availability, your design point might have to require measurements by a processing capability that is independent of the operating environment. So that problem, that very constrained problem of instant availability, has not been solved yet in the field. There are ideas about how to do it. I'll leave it at that. I think that's where he was going.
Thank you. Monty, quickly, can you tell us when you expect the TSS layer API to be available? That was a question from an attendee.
Yeah, well, the system API, which is pretty much a one-to-one C function to TPM function, is actually publicly available now. We would certainly hope the more application-friendly layer to be available sometime this year.
Okay, thank you. Stacy, can you talk a little bit about what role Windows 8 and Windows Server have with the TPM?
Okay. Well, one of the things I didn't mention when I was talking about Windows 8 is that On the endpoint, on PC endpoint, BitLocker is the killer application for TPMs. BitLocker requires a TPM in order to validate the integrity of the BIOS of the platform. And in research that was done on trying to get at some idea of how popular BitLocker was when Windows 7 came out, over half of all of the questions on the tech forum for security at Microsoft were about how do I use BitLocker. So that's one of the ways that TPMs are used. Also on an earlier slide, I spoke about measured boot, which includes a hash measurement of all of the firmware, the OS loader, and the early elements of the operating system that execute prior to the start of security services. So that's one of the most critical functions, or one of the most critical uses of the TPM in Windows 8. Also, Microsoft has chosen to implement virtual smart card capability in Windows 8, depending on the TPM as that smart card. So any cryptographic keys that you are protecting using the virtual smart card capability in Windows 8 are actually protected for you by the TPM. And I think they have some other values that they intend to roll out in the future. They intend to make some system-level calls available for application writers who want to take advantage of the TPM in the system as users of the TPM, not as administrators. One of the differences between 8 and prior versions of Windows is Microsoft owns the TPM in 8. So I'll leave it at that.
Thanks. And we have time for one final question, and this is for you, Monty. Besides protection of keys, passwords, and certificates, what else can the TPM do that is useful?
Well, you can. It's got NV storage, or we call it NV storage, but the NV storage has basically all the security properties that you can do with keys. So outside of what Stacey mentioned, we've got virtual smart card type applications. You can also use it for storing information, either in integrity or confidentiality matter, just bulk information. So that's kind of a general purpose that usage that we added to it. So there's a number of them as well, but that's the first one that wouldn't be obvious.
Great, and I think that's all the time we have today. We'd like to thank you for attending this TCG webinar, and we will follow up with you on any direct questions that were not answered during the live event. Thank you. Goodbye.